Colleagues, our guests, ladies and gentlemen, on behalf of the Vice Chancellor and Principal, Professor Nanapoku, it gives me great pleasure to welcome you to the inaugural lecture of Professor Shaun Ramroop. The Vice Chancellor conveys his congratulations and best wishes to Professor Shaun Ramroop. Inaugural lectures form part of the university's public lecture series and may only be presented by newly appointed full professors who have been appointed in academic schools and centers. Inaugural lectures present an opportunity for showcasing the exciting and groundbreaking research and teaching being carried out by professors in our university. Each lecture represents a significant milestone in an academic's career, providing official recognition of their promotion or appointment to full professorship. These lectures are furthermore an ideal opportunity for new professors to introduce themselves and to present an overview of their own contribution to their field to academic peers, students, and research collaborators. Inaugural lectures are also a platform for celebrating a professor's academic achievements with his or her family, friends, mentors, and colleagues. At this juncture, I would like to also acknowledge the following guests: members of the executive management, members of Senate, our inaugurant this afternoon, Professor Shaun Ramroop, family and friends of Professor Ramroop, academics and professional staff, students, alumni, and distinguished guests. It is now my pleasure to introduce our Dean and Head of School, Professor Delia North, who will now formally introduce the inaugurant, Professor Ramroop.
Good afternoon, Deputy Vice Chancellor, Registrar, academic staff, ladies and gentlemen. It is my extreme honor to introduce Professor Shaun Ramroop, who will be delivering the inaugural lecture this afternoon, titled Missing Data Within the Ambit of Flexible Statistical Modeling. However, before I hand you over to Professor Ramroop, it's my absolute pleasure to tell you a little bit more about this remarkable statistician. Professor Shaun Ramroop is a full professor of statistics in the School of Mathematics, Statistics and Computer Science on the Pietermaritzburg campus. After completing his BSc, majoring in statistics and applied mathematics, in 1995, he went on to complete his honors degree in statistics in 1996. Upon graduating, he was employed as a biometrician by the South African Sugar Research Centre in Durban. Professor Ramroop's academic journey started by him being employed as a statistics tutor in 2001 at the former University of Natal on the Pietermaritzburg campus. After completion of his master's degree in statistics through UNISA, he joined the UKZN statistics sector on the Pietermaritzburg campus in 2002. Since his first days as a young academic, he has been extremely highly regarded, both by students and fellow academics in his discipline, as an excellent teacher, but also researcher. This standout academic from the former School of Statistics and Actuarial Science has continued to grow over the years. He obtained a PhD in statistics in 2007 and was promoted to the level of senior lecturer in 2011 and associate professor in 2016. And we are here today to celebrate Professor Ramroop as a full professor of statistics, a title he earned in 2020. One of the standout features of Shaun Ramroop is his teaching ability. Therefore, he got the award of Distinguished Teacher within the College of Agriculture, Engineering and Science in 2020, and that came as no surprise to colleagues and students that interact with him. The rise through the academic ranks, of course, is testimony not only to being a good teacher, but also to being an accomplished researcher. Professor Ramroop has graduated 25 students with a master's degree in statistics and 6 PhD students. He has published more than 50 papers in accredited journals. His research areas include biostatistics and statistical modeling and analysis as applied to business, health, education, environment, agricultural settings, and social systems. His research has further led to the application of novel models for meaningful inference to inform the underwriting of policies and extending the existing body of knowledge in the mentioned research areas. In particular, from 2016 to 2017, Professor Ramroop was the chief consultant researcher to the Msunduzi municipality in the Living Conditions Survey. His role involved training field workers, design of a survey, analysis of results, and presentation of findings to stakeholders in the Msunduzi municipality. He was the chief statistician to the Greater Sekhukhune District Municipality in their customer satisfaction survey from 2012 to 2015, and the Sulumanzi Water Project from 2013 to 2016. He has led many research projects linked to business and industry. These many projects he has undertaken have infused his research and supervision skills to the extent that he's been recognized as one of the top 30 emerging researchers at UKZN for the 2010th year. Professor Ramroop is not only a top teacher and very accomplished researcher with a strong focus on solving real problems that arrive in industry and municipal government settings, but he has a mindset to serve his discipline, both at local, by that I mean UKZN, and national level. Evidenced by the fact that Professor Shaun Ramroop joined the leadership team of the School of Maths, Stats and Computer Science as academic leader of statistics for the period 2017 to 2020. He offered his services to the South African Statistical Association, where from 2012 until present, that's a long time, he's been a judge of the South African Statistical Association annual honors project competition. Professor Ramroop is thus in a position to assess the standard of the best honors projects in statistics from across the country, and that provides rich feedback that UKZN continues to benefit from. The knowledge gained by Professor Ramroop in this key role has really been so important because it's helped the discipline of statistics to strategize, to find out how to set high standards for the honors project topics in the discipline here at UKZN, ensuring that our graduates are marketable and sought after by external institutions, business, and industry. Professor Ramroop is further a key factor to the success that the postgraduate programs in data science have achieved at this institution. Ladies and gentlemen, it's my absolute pleasure to hand you over to Professor Shaun Ramroop to deliver his talk titled Missing Data Within the Ambit of Flexible Statistical Modeling. And now you will hear why students regularly comment on his beautiful teaching voice. Over to you, Professor Ramroop.
Good afternoon to the DVC, Prof. Maudi, my Dean, Prof. North, members of the academic community at UKZN, friends, family, collaborators, students, and members of the public. Greetings and salutations to you, and welcome to my inaugural lecture, which I've titled Missing Data Within the Ambit of Flexible Statistical Modeling. The contents of this inaugural lecture comprise of an introduction, my past and present research, missing data, which is broken down into missing data mechanisms, missing data tests, missing data methods, and then there will be an application of merging of my past and future research. Some future research ideas will be presented, and then of course there'll be acknowledgement and appreciation. As an introduction, Most data is usually analyzed as complete case analysis, and the missingness is often ignored. This often leads to incorrect statistical inference and poor conclusion. The bottom line is that missing data analysis is becoming an essential and integral part of sound statistical analysis. For most of my research, I found that statistics practitioners and statisticians often venture into analysis only on complete data because it's favorable, and any data that is missing is deemed to be abnormal and is usually deleted by many statistics practitioners. My past and my present research includes the following. During my past research, where did it all begin? It began in my PhD with respect to the respiratory syncytial virus in a longitudinal setting and finding ways of estimating the force of infection and the rate of recovery. This seminal work was published in a prestigious journal entitled Statistical Methods in Medical Research. This has given rise to flexible statistical modeling in various other fields. For example, my present research and contribution via a sample of papers and areas include malnutrition and poverty in children under 5 years old, finance, anemia, childhood anemia. This is more recent with one of my PhDs, Chris Kulu, malaria, contraceptive use amongst women, food security, and happiness studies as well. Flexible statistical modeling has been a critical starting point and continues to be so in my career. And it is a place where missing data has now found its application and its seat at the table of statistical analyses. So where did it all begin, or where did it all begin? The respiratory syncytial virus study was part of my PhD work at the beginning of my research. First of all, what is the respiratory syncytial virus? This was first discovered in chimpanzees by Morris and his colleagues in 1956, and Channock in 1996 associated RSV with bronchiolitis and lower respiratory tract infection with infants and children. It is one of those viruses that causes acute coughing and can often lead to bronchitis and in certain cases, severe pneumonia. In some parts of the world, RSV is known to have more fatalities than HIV/AIDS has. Say, for example, in certain parts of Europe and also in Africa, to the surprise of many health practitioners. All races appear susceptible to the respiratory syncytial virus with similar disease patterns. The peak incidence of occurrence is observed at 2 to 8 months in infants. And hence this study was very critical in providing healthcare practitioners with relevant information so that they would be able to develop certain intervention strategies to combat the virus, as it is also an airborne virus. Hospitalization occurs in 0.1% to 2% of infants under the age group of 1 year annually, and overall between 3.5 and 4 million children under the age of 4 years acquire an RSV infection. In the USA, more than 100 children are hospitalized annually, and virtually all children have had at least one RSV infection by the 3rd birthday. Males and females are equally affected by the respiratory syncytial virus. These statistics are important because they give us some kind of description and visual about our problem setting. The Khalifi RSV study was a repeated measurement or longitudinal study or longitudinal data set measuring the presence or absence of RSV in children in coastal Kenya. And the study took place over 15 consecutive months, involving children from 0 to 15 months. This certainly tugs at your heart because children are often helpless at this age and rely heavily on medicine and the intervention strategies that biostatistics can possibly provide for it. 368 children or infants were measured at unequally spaced time intervals. The variables that were recorded on each child include whether or not a child is infected, a visit which comprised 44 visits, the time between the visits, which is some Dij, measured as the difference between Tij and Tij minus 1. The type of sampling was active, whether the field worker went to visit the child, or passive, if the child was brought to the study hospital to be sampled. Time in months was measured since the beginning of the study, and there was the prevalence of the virus in the blood. In all, there were several children that were measured at each of the different times. A child measured varies from one child to another. And a child can move through the following transitions. So if a child was uninfected, they could remain uninfected over a period of time. In other words, this was coded as a 0, transitioning or moving to or followed by another 0. From uninfected to infected, a child moves from a state coded from 0 to 1, infected to uninfected from 1 to 0, and infected to infected from 1 to 1. A summary of these disease transitions is best summarized in the table that is in front of you. And we can see that we had a lot of transitions from 0 to 0, where we moved from uninfected stage to uninfected stage. And we had 132 transitions from a child being uninfected to uninfected, and 131 transitions from a child being uninfected to infected. The other big issue with the Kalifi data set that was ignored was that there was a lot of dropout, or what we call attrition. And this leads to a common form of missingness. For example, if we see the child at visit 1 was present for the first 5 visits and then dropped out from visit 6 to visit 44. Child 2 on the second was present, on the second row was present from visit 1 to visit 4 and dropped out from 5 to 44. And this pattern continued throughout the entire data set. Why does dropout occur, you might ask? Well, there are several reasons why dropout can occur in any experiment, in any clinical trial, in any survey. But some of the reasons why dropout occurs are due to the fact that there might be death of individuals, adverse reactions, unpleasant study procedures, lack of improvement, early recovery, and other factors related or unrelated to trial procedure and treatments. And missing data in a study because of dropouts may cause the usual statistical analysis for complete available data to be subject to potential bias. And one of the problems in the Kalifi data set was that we found that 35% of the data was actually missing. So before I go into the missingness, which will then be espoused from this past research to the future and present research, White, who is an epidemiologist in 2005, estimated the force of infection, some lambda, and rate of recovery, some upsilon, using a mathematical model or a set of differential equations as follows. She and her colleagues found that the force of infection was 0.0135 with a standard error of 0.001, and the rate of recovery as 0.4979 with a standard error of 0.067. Now, this is what we call the deterministic approach, and most applied mathematicians would recognize this as being part of an estimation procedure from a set of differential equations. The problem is that differential equations does not account for missingness, as is the case in this data set. So we embarked on a research journey on developing statistical methods on how to firstly estimate the force of infection and the rate of recovery using statistical methods. And this is called a stochastic approach. So this research was novel in the sense that it married the applied mathematics approach, which is deterministic, with the statistical methods approach, which is stochastic. And this is very rare to see. Before we get into how we solve the problem, the questions asked in this study was, can the force of infection and rate of recovery be estimated using statistical methods? The force of infection is simply defined as the inverse of the average time to infection of the susceptible hosts, whilst the rate of recovery is the inverse of the average duration of infection. Both the force of infection and the rate of recovery are measured in days to the -1. So some of the challenges in estimating the force of infection and rate of recovery is that they are not observed. In other words, there's no data, there's no column or variable of data that was presented to us. So conventional models such as marginal models, random effects models, transition models have to be adapted or modified. The response variable is incomplete. It has about 35% of missing data. And then there's a true disease process versus observed disease process. In other words, a child can become infected and then uninfected and then infected again and then stay uninfected and become infected again and finally reach the hospital. This leads to the fact that there is an underlying or latent process that's happening here. As far as the RSV data is concerned, statistical methods have not been used to estimate the force of infection and rate of recovery. And there is the issue of dropout, which we will discuss a little bit later on. So how then did we estimate the force of infection and rate of recovery? We firstly went to the susceptible, infected, susceptible model, which is a common model in biostatistics and epidemiology. Basic governing differential equations is given as the partial of the Q of A of t with respect to t plus the partial of Q of A of t with respect to A, where A and T represent the proportion of susceptible and infected individuals at time t and age A, is equal to minus the force of infection, which is a function of age and time, times the Q of A of t, plus the rate of recovery, which is a function of age and time, times the P of A of t. Note that the Q of A of t and the P of A of t always sum to 1. The transition probabilities from the SIS model are defined as follows. The probability of going from uninfected to uninfected is defined as e to the minus lambda times the time between visits, dij. The probability of going from uninfected to infected is 1 minus e to the minus lambda times dij. And the probability of going from infected to uninfected was 1 minus e to the minus upsilon times dij. And infected to infected is e to the minus upsilon times dij, where dij is the time interval between the visits at time tij and tij minus 1. What we had discovered, or what I had discovered, was that the best way to estimate the force of infection and the rate of recovery was via a full likelihood. And the likelihood that we developed was the product of all the infections from 0 to 0, or uninfected to uninfected, times the product of all transitions from uninfected to infected, multiplied by the product of all transitions from infected to uninfected, and then from infected to infected. And in the front of that product, you find that this is a starting place of the child where you have P naught of 1 raised to the power zeta, all into 1 minus P naught of 1 raised to the power 1 minus zeta, where zeta is an indicator variable denoting the initial state of the child when the child is initially infected and 0 otherwise. Hence, the P naught of 1 is the probability that the child is initially in the infected state such that the P naught of naught is 1 minus P naught of 1. So what do we do after this here once you've developed the likelihood? We could then take the log of the likelihood, which is very common in statistical inference, and take the partial derivative with respect to lambda and the partial derivative with respect to upsilon. And using the Fisher scoring method, we now developed an iterative method to solve for the parameters. The maths is rather elegant and separates itself out rather beautifully. A program was written in SAS using prop IML, and the following estimates were then developed using statistical methods as a confirmation to the differential equations estimates. and we found that they were almost 100% in uniformity with those estimates. And this excited us extensively. The only problem was that we had not dealt with the missing data. And 35% of the data that was present in the original set was missing. The estimates that you saw on the previous slide was only for the complete case analysis. So now we have to deal with the missing data. And this is where my present and my future research began. Missing data can be as a result of three missing data mechanisms. The first of which is missing completely at random. And this is where the missingness does not depend on the values of the data. Why? Missing or observed. So you have the probability of the PDF of missingness given the observed and the missingness is just equal to the PDF of M given some phi for all Y. And the data is said to be missing completely at random. Perhaps a simpler way of explaining this is that the missingness does not depend on the data values. As an example, imagine a research associate shuffling raw sheets and arbitrarily discarding some of the sheets. This would then constitute data which is MCAR. Another example of data which is MCAR arises when investigators randomly assign research participants to complete 2/3 of a survey instrument. Cases with complete data are indistinguishable from cases with complete data. So missing completely at random does not depend on the observed value, but depends on other mechanisms. Missing at random, which is by far the most common form of missingness. If Y observed denotes the observed components or entries, and Y miss the missing components, when the missingness just depends only on Y observed, the observed components or entries are then missing at random. Symbolically or mathematically, this can be written as the F of M given Y and phi is just equal to the F of M of the observed data given phi for all the missingness. For example, if you consider research participants with low self-esteem, they are less likely to return for follow-up sessions in a study that examines anxiety level over time as a function of self-esteem. Murray and Findlay in 1988 developed a set of hypertensive drugs measuring diastolic blood pressure. As soon as the blood pressure was too high, participants were asked to drop out. The dropout is then due to the missing, or the dropout is then due to the observed values. It depends on the values of the blood pressure before the dropout. This is missing at random. And then, of course, we've got the most complicated form of missingness, which is not missing at random. When the distribution of the missingness data indicator matrix depends on the missing values on the data matrix, we have that the missing data mechanism is called not missing at random. This type of missingness is often called non-ignorability. And the pattern of data missingness is non-random, and it is not predictable from other variables in the database. The point of considering missing data mechanisms is that you have to understand what type of missingness you have in your data before you start to work with it. One of the ways in which you could deal with this is testing for the missing data mechanism. Now, if your data is assumed to be MCAR, one could test for this using Little's test, which utilizes logistic regression. This was developed in 1988, Ridout's test in 1991, Park and Davis in 1993, and Hatchen and Bassel in 1996. These are 4 different tests which could be performed on your data to assess the mechanism of missingness before any missing data methods are carried out. You could have missing at random. This is not testable, but can be done in the presence of other distributional constraints. Most of the methods that are used in statistics that are based on likelihoods. For example, generalized linear models, linear mixed models, generalized linear mixed models, generalized estimating equations are all likelihood-based models. And very often these carry the assumption of missing at random, and it holds true 99% of the time. You would have seen in the aforementioned slides that we had developed a likelihood. And if you have been following, an astute student would have suddenly discovered that the method we used would have carried the assumption of missing at random. Missing not at random or not missing at random, Molenberg's, Goedegebeer, and Lipsitz in 1997 have developed a test for assessing this mechanism and its validity. Here we come to the missing data methods, and this is somewhat of the crux of my inaugural lecture and represents much of my present and future research. The first method is called last observation carried forward, or LOCF. LOCF is popular amongst practitioners because it is simple to put into effect. LOCF assumes unrealistically the missing data after the subject withdrawal are the same as the last observed value for that particular subject. There is a bias in results, and inference, misrepresentation of the underlying process, and you find that there is a great loss of information. So for example, if we had this scenario where a child was from visit 1 to visit 6 observed, and you find that the last state of the child was uninfected, denoted by 0, then from visit 7 to visit 44, we would simply fill in or plug in the gaps with a set of zeros. I ask you how realistic this is really in any statistical analysis and in any scientific setting, how realistic this is. Then there is complete case analysis, which is what we did in my original research. This restricts the analysis to those subjects for which all information has been measured according to protocol. The claimed advantages include computational simplicity. You must be joking. Complete case analysis can be very, very complex. The only drawback it has is loss of information from deleting the missing data. There's no need for a full longitudinal model. This is one of its byproducts. This method may not answer all the scientific questions, and it can assume missing completely at random in the case of weighted generalized estimating equations. A more popular and commonly adopted method of handling missingness was introduced as multiple imputation. The idea of multiple imputation was formally introduced by Rubin in 1978. Later, Rubin and Little gave it comprehensive treatment. It requires a missing at random assumption, which is in line with all likelihood-based models within the ambit of flexible statistical modeling. And the procedure is very simple. The missing values are filled m times to generate m-complete datasets. The m-complete datasets are analyzed using standard procedures. The results from the analysis are combined into a single inference. Rubin suggested the use of 5 datasets combined into one complete dataset. Technically, one would use software. For example, in SAS, you would use ProcMultMI at step 1 and MI-Analyze at step 3. Other software include MICE with S+, ICE in Stata, and iVoy with SAS. R has also got very attractive features that accommodate multiple imputation. The drawback with multiple imputation is that it assumes the data set to be one large matrix and assumes a multivariate normal distribution. This is unrealistic if you've got categorical data such as gender, dichotomous data such as gender, nominal data such as race group, and various other variables, because it would round off your imputed values, and this would often result in truncation, round-off error, and can also lead to the lack of convergence by using certain algorithms. The multiple imputation procedure can also make use of the EM, or expectation maximization algorithm. To overcome this problem, Van Buren in 2007 extended the idea of multiple imputation to multiple imputation via chained equations. And we abbreviate this as MICE. Since we're dealing with transitions in our scenario with the RSV dataset, they are discrete values, and there's a risk issue of truncation. I've mentioned this already, as well as the multivariate normal assumption, which can be violated. So in very simple English, if you have data that's ordinal, if you have data that is discrete, if you have data that is nominal, you cannot use conventional multiple imputation, such as regression-based imputation, mean-based imputation, nearest neighbor-based imputation, and so on and so forth. One has got to step over to multiple imputation via chained equation. Multiple imputation via chained equations is a semi-parametric and flexible alternative that specifies a multivariate model by a series of condition models, one for each incomplete variable. And the basic idea is actually quite old and is also known by a variety of names such as stochastic relaxation, variable by variable imputation, regression switching, switching regressions, ordered pseudo-Gibbs sampler, incompatible MC, iterated univariate imputation, and chain equations. In simple English, we have to impute each variable one at a time as a variable by variable basis, best specifying an imputation and distribution per variable. And I've alluded to that in my third bullet here. It is an attempt to define the probability distribution of y, x, and r by specifying a conditional distribution or deviation from what the probability of yj given the missingness for each yj. And the density is to impute the missingness given the rest of the variables. So starting from a simple guessed values, imputation under FCS is done by iterating over all conditionally specified imputation models. Very simple, very useful, and a common sense approach to handling all kinds of data types. There is also more recently subset correspondence analysis, or SCA. This technique was not widely used, but is becoming increasingly popular. SCA is used extensively for categorical data, especially in contingency tables. And the technique was actually popularized by Green and Thorough in 2004, and then Greenacre previously in 1992. The technique becomes contentious when the missingness per variable is more than 30%. And this is its limitation. You would have also picked up by now that the missingness we had in my original work was 35% and above. So SCA may not perform as well as we expected to do so. The procedure for SCA is simple. We start off with the contingency table and convert the data into row and column profiles, taking each observation and Nij and dividing it by the overall total. We then work out the row and column profiles, Ri and Cj. And using these, we work out standardized residuals, Pij subtracting product of Ri and Cj over the square root of Ri and Cj. And this is some kind of standardization process. Where SCA differs from the conventional correspondence analysis is that it is interrupted, and from the matrix S of standardized residuals, we then select the rows and columns that make up the subset of variables or categories chosen to be included in further analysis with the missingness. And finally, these variables are used to develop new principal coordinates, and we take them and plot them in some kind of a biplot to get some kind of a picture. And this helps us from the principal components to develop estimated values for missing values. The other method that has also not been used extensively, but is also now becoming very, very popular, is inverse probability weighting, or IPW. This requires an MER assumption and is perhaps the oldest and technically simplest. It makes use of the Horvitz and Thompson survey sampling estimator, and it's based on the idea of a weighted analysis, which compensates for the over and underestimation of the missingness. It's similar to the idea of raking in handling missing data in sample surveys, and the process is simply replacing the mean with the weighted mean, where the weights are the reciprocal of the probability of observation. So, just as an example, the weights are developed, are then taken and used in a new analysis. Suppose we have Group A, Group B, Group C with the full data observed as 1, 1, 1, 2, 2, 2, and 3, and 3. And then we observed a value of 1 for Group A. There were 2 missing observations. Group B was fully collected, and Group C had 1 missing observation and a value of 3 observed. And you can see the weights assigned was 1/3. We don't have weights for the missing data. Group B has all of its data, so there's no need for weights, and Group C has got 1 observed value or datum and 1 missing value. So how do we do this here? In simple English, the idea is to develop a weight for the observed value to compensate for the missing values. And the weight is then used in any conventional analysis to accommodate overestimation, underestimation, loss of information, and correctly give you a proper statistical conclusion. The original weight for the first observation in group 1 was actually 3, but the new weight would be 1 times a third plus 2 plus 2 plus 2, that's the observed data, times 1, because these carry a weight of 1, always observed, plus 3 plus 3 plus 3 times 3 over 2, which is the weight for that particular observed value, which was 1 over 2/3. And this is divided by the total weights. Remember, it is the probability is 1 over the weight is 1 over the probability. So it's 1 over 1/3 plus 1 over 1, 1 over 1, 1 over 1, plus 1 over 2/3, 1 over 2/3. And this works out to give us a weight of 2 for the first datum, which was 1. Likewise, we would work out weights for the observed value in group C, and then we would run our analysis. So the set of weights is a very useful and becoming a very, very integral part of missing data analysis and carrying out all kinds of analyses by using these kinds of weights. And these help us to cater for any kind of bias that may be incurred in the analysis. What I did next was that I actually went and took the original Kilifi data set, which I had used many years ago, applied complete case analysis, worked out LOCF to accommodate for the missingness, multiple imputation via chained equations for the missingness, subset correspondence analysis, and also inverse probability weighting. Now, the idea is for us to look at the standard errors. The smaller the standard errors, the more effective and the more accurate our estimates are. And one can see clearly here that LOCF, in comparison to the complete case analysis, and with the estimates that Lisa White and her colleagues achieved, is least consistent with all of the analyses. And therefore, I do not recommend LOCF to be used in any scientific setting. It can be used as a comparative tool, or it can be used under strict supervision and advice of suitably qualified statistics practitioners. MICE is extremely consistent with rather low standard errors, and so is inverse probability weighting. The standard errors are much in line with MICE method. Subset correspondence analysis is uniform, except that it gives us slightly inflated standard errors. And it is not surprising to me that this is so, because subset correspondence analysis performs very well when we have 30% or less of our data missing. And in our case, we had 35% and above missing. So we can see that the champions of handling the missingness in this particular data set was none other than multiple imputation via chained equations and inverse probability weighting. My conclusion: statistical methods for estimating the force of infection and rate of recovery are just as good as other methods of estimation for this type of scientific setting. The direct likelihood estimation, maximum likelihood approach gave similar answers and espoused statistics and applied mathematics, and gave us a further insight into the power of stochastic approximation by incorporating missingness into the analysis. Multiple imputation and inverse probability weighting gave the most consistent estimates when compared to the available data. Viable method to handle dropout. I strongly recommend these. LOCF is dangerous and should be locked up and put into jail. I'm just kidding. It artificially inflates the correlation between successive time points and is unrealistic, as I've already mentioned. In this scientific setting, LOCF underestimated the force of infection. Well, what about future research, you might say? My future research, and with the advent of the fourth industrial revolution, possibly the fifth industrial revolution, with the advent of data science, data mining, data analytics, the area using missing data mechanisms for NMAR, which I did not consider, would require what we call selection models and pattern mixture models. These are being developed at an accelerated pace by statisticians all over the world. The other extension to large data sets in data science is multiple imputation with propensity score models and multi-level multiple imputation. With the advent of big data, data mining, etc., more computationally advanced methods such as machine learning methods, neural nets, and hybrid data-driven models are being used. One of the algorithms that's gaining popularity is the greedy algorithm, and several other algorithms that are related to nearest neighbor methods of estimating missing data using cluster analysis techniques. There are also a lot of advanced algorithms that compete with the expectation maximization algorithm, which was developed by Laird, Ware, and Dempster in 1970 odd. So the future of missing data is here to stay. And my recommendation is that anyone who is a budding statistician or statistics practitioner will have to somehow do a course or become au fait in the area of missing data to be espoused to every other area of statistics and statistical analytics to ensure that your repertoire is fully functional and very, very strong. My acknowledgements and appreciation. Nobody appears at a particular level in their career and in their life without the help of people around us. And first and foremost, I want to acknowledge my Lord and Savior, Jesus Christ, without whom I am nothing. And I publicly confess him this afternoon. John chapter 3, verse number 30 in the Bible says, he must increase and I must decrease. May his name always be glorified in my life and in the life of my family. I also want to place on record my sincerest thanks to my wife and children, Shani, my son Elisha Benjamin, my daughter Rebecca Grace Ramroop. I could not have asked for a better family, and I thank you profusely this afternoon and acknowledge you. To my late parents, Mr. and Mrs. S. Ramroop, who are arguably the hardest working people I've seen in my entire life, I thank them and for all the values they've instilled in me and my family. I also acknowledge my sister Risha and extended family and my in-laws as well to the Kalidas family. From an academic point of view, I want to acknowledge a few people. Professor Temeskin Zawata, who mentored me in the initial stages of my research and taught me how to use PROC-IML. I salute you and I thank you that we are brothers, colleagues, and co-laborers in Christ. Prof. Delia Nort, a pioneer and a stalwart in our school, somebody with such a big heart. I thank you for leaving the indelible marks of your entire philosophy and thinking upon my life. Thank you, Prof. Delia. Prof. Henry Wambi, who was my supervisor for my PhD, and I was his first PhD student. Thank you, Prof. Henry. We continue to collaborate, and your work was a seminal work that led to so many other pieces of work for us. Dr. Faustin Habjarimana, I acknowledge you. He was my PhD student, my postdoc, and eventually my colleague. I want to thank you because your PhD was a seminal work that formed the basis for other work and a foundation for many, many icons of great research to be explored. Thank you, Faustin. To all the staff at Westville and PMB in the statistics department, Reshis Chifurira, our AL, Oliver, Seleshi, Tabo, Jessica, Knowledge, Javed, Mike Murundeni, Daniel Nombuso, Sue, Natalie, and Zelalem, thank you. And thank you for contributing in every stage of my life. To our administrators, Ifine Hayes, who is now retired, but she was employed in 2000 when I was first employed at the university. I thank you, Ifine, for making my stay great and for helping me every step of the way. Currently, our administrators, to Bev and Aleshni, thank you for everything. I acknowledge you. School operation manager and technical staff, Jackie White, Sean Woodley, and Leonard Else, thank you for everything, and I acknowledge you and appreciate you. To our cleaner, Sibongile Aida, with whom I have got a 15-year relationship. I also want to acknowledge Sibongile and thank you for touching my life in some way or the other. To UKZN and the executive leadership from our VC, DVC, and many other people, thank you for putting faith in me and giving me an opportunity to work at a prestigious institution like UKZN. To my spiritual family at the campus church, I love you and God bless you. Thank you for touching my life. To Pastor Bill Naidu, who is late, Pastor Jay Naidu is late, and all of the pastors of my previous church, Bethel Assembly, I acknowledge you and salute you for imparting some grace into my life. To my spiritual father, Dr. S.Y. Govender, thank you for imparting grace and being a mentor to me. God bless you always. To all my students and collaborators, past and present, I acknowledge you and salute you for all your contributions that you have made to my career and touched my life and my humanity in some way or the other. To Pamela and her team, thank you so much for putting this entire thing together. I am done with my talk. Thank you to everybody who attended today, and may God bless you always. Thank you very much.
Thank you very much, Prof. Ramroop. I don't know what to say to confirm what you've just made all of us believe. Those of us who are non-believers now believe that statistics is everything. It's amazing how you were speaking to everyone in every profession about the relevance of statistics and the importance of statistics. It's a wonderful area of study. Everyone in this university can benefit from it. We are very much blessed to have someone like you in this university. We know that you're going to remain with us for the rest of your life. You're not going anywhere. Of course, you listed everyone that needs to be thanked. I'm not going to repeat that, but I have to reiterate our utmost thanks to your parents, to your late parents, and your wife and children for allowing this university to share such a wonderful asset with UKZN. Colleagues, thank you very much for spending your time with us today. We had a wonderful afternoon listening to this amazing talk. I'm sure many of us are going to start thinking about the future directions in statistics. Thank you to everyone who was involved in organizing this meeting successfully for the millionth time. Wonderful team of corporate relations and the Office of the Registrar. I'm sure you're going to leave today remembering this course and thinking about it as a future direction for everyone in our university, in all colleges. Statistics, go statistics, go. Viva statistics, viva. Thank you very much, colleagues.
Well done, Shaun.
Thanks, Celia. Thanks, Prof. Modi.
Hat Mesken.